The James Webb Telescope just deepened the greatest mystery there. Are moments in history when humanity invents a new way of seeing. The telescope was one such moment. Suddenly, the stars were no longer points of light decorating the night sky. They became worlds, galaxies, vast structures stretching far beyond imagination. Every leap in our ability to observe the universe has done something remarkable. It has answered old questions, but more importantly, it has revealed better ones. For thousands of years, the night sky appeared unchanging. Ancient civilizations looked upward and saw patterns that inspired myths, navigation, calendars, and philosophy. The stars seemed fixed against a dark canvas, distant yet eternal, offering little hint of the immense complexity hidden beyond human sight. Every generation inherited the same celestial view, believing that what the eye could perceive represented the true extent of the universe. Yet history has repeatedly shown that whenever humanity develops a new way of observing nature, reality becomes far larger, stranger, and more fascinating than previously imagined. The invention of the telescope marked one of the greatest turning points in human history. For the first time, people could see mountains on the moon, moons orbiting Jupiter, and countless stars invisible to the naked eye. These discoveries transformed our understanding of the cosmos, replacing an Earth-centered picture with one in which our planet occupied only a tiny corner of a much greater universe. Each improvement in telescope technology extended that transformation, revealing spiral galaxies, exploding stars, enormous clouds of gas, and distant clusters containing hundreds of thousands of galaxies. Every new instrument pushed the horizon farther away, proving that the universe always held more than we expected. The James Webb Space Telescope represents the latest and most ambitious step in that long journey of exploration. Unlike traditional telescopes that primarily observe visible light, Webb is designed to detect infrared light, allowing it to see objects hidden behind clouds of cosmic dust and to capture faint signals that have traveled across space for billions of years. This capability is essential because the expansion of the universe stretches ancient light into longer, redder wavelengths. By observing infrared light with extraordinary sensitivity, Webb effectively opens a window into an era that had previously remained beyond humanity's reach. Looking deeper into space is also an act of looking backward in time. Light does not travel instantly. It moves at a finite speed, covering nearly 300,000 kilometers every second. Although that speed is unimaginably fast on human scales, the distances between galaxies are so enormous that light often requires billions of years to complete its journey. When Webb observes a galaxy located more than 13 billion light-years away, it captures light that began traveling shortly after the universe itself came into existence. Instead of seeing these galaxies as they are today, the telescope records them as they appeared when the cosmos was still in its earliest stages of development. This remarkable ability transforms the telescope into a kind of cosmic time machine. Rather than relying solely on theoretical models or computer simulations, scientists can directly examine evidence from epochs that were once inaccessible. They can study the birth of the earliest stars, trace the assembly of the first galaxies, investigate how matter began organizing into large-scale structures, and observe processes that unfolded only a few 100 million years after the Big Bang. Every observation provides another fragment of a story written across the history of the universe itself, revealing ancient chapters that remained hidden for billions of years. One of the primary goals of the James Webb Space Telescope was to observe the earliest galaxies ever formed. Based on decades of theoretical research, astronomers expected these ancient systems to be small, faint, and relatively simple. The universe had only recently emerged from the Big Bang, leaving limited time for gravity to gather enormous amounts of matter into fully developed galaxies. According to established models, the first galaxies should have resembled modest collections of young stars, gradually growing through collisions, mergers, and the steady accumulation of gas over hundreds of millions of years. Webb was expected to confirm this timeline with greater precision than ever before. Instead, many of its earliest observations revealed something astonishing. Among the faint points of light were galaxies that appeared unexpectedly bright, surprisingly massive, and remarkably well organized. Rather than resembling fragile cosmic infants, some looked more like mature systems that had already experienced extensive periods of star formation. Their size, structure, and apparent abundance challenged predictions that had guided modern cosmology for years. Scientists were not expecting to find galaxies with these characteristics so soon after the beginning of cosmic history. Brightness is one of the first clues astronomers use to estimate the nature of distant galaxies. A brighter galaxy often indicates the presence of a large number of stars or an intense burst of star formation. Webb detected objects whose luminosity suggested they had already produced enormous stellar populations within a relatively short span of cosmic time. If these interpretations are correct, then the processes responsible for creating stars in the early universe may have been far more efficient than previously believed. Such rapid growth raises important questions about how gas collapsed, cooled, and transformed into stars under conditions that existed only a few 100 million years after the Big Bang. Mass presents another puzzle. Theoretical models describe galaxy formation as a gradual process driven by gravity. Small structures emerge first, eventually combining to form larger systems over immense periods of time. Yet several galaxies observed by Webb appear to possess masses that seem difficult to reconcile with this slow evolutionary picture. If galaxies accumulated matter more rapidly than expected, scientists may need to reconsider the rates at which gas flowed into these systems, the influence of dark matter, or the physical conditions that governed the earliest stages of cosmic evolution. Their apparent maturity is equally intriguing. Mature galaxies often display organized structures, stable populations of stars, and evidence of complex internal development. Finding such characteristics at an unexpectedly early time suggests that galaxy evolution may have progressed much faster than existing theories predicted. It is possible that the first generations of stars lived and died with extraordinary speed, enriching surrounding gas and accelerating the formation of subsequent stellar populations. Another possibility is that the environments of the early universe created conditions unlike anything observed in later cosmic history, allowing galaxies to assemble with surprising efficiency. These discoveries do not necessarily mean that our current understanding of cosmology is incorrect. Scientific interpretation requires careful analysis, additional observations, and independent verification. Some galaxies initially believed to be extraordinarily ancient have later been assigned different distances after more detailed measurements. Others continue to support the idea that the early universe was capable of producing unexpectedly large and luminous systems. As Webb gathers more data and complementary observations from other observatories become available, astronomers continue refining their measurements, testing competing explanations, and comparing new evidence with increasingly sophisticated simulations of cosmic evolution. Throughout history, some of the greatest breakthroughs in science have begun with observations that refuse to fit established theories. This pattern is not a flaw in the scientific process, but one of its greatest strengths. Scientific theories are not permanent truths carved into stone. They are carefully constructed models that explain the evidence available at a given time. As new observations emerge, those models are tested again and again. When the evidence agrees with predictions, confidence in the theory grows. When reality refuses to cooperate, scientists are presented with an opportunity to investigate deeper, refine existing ideas, or develop entirely new ones. The James Webb Space Telescope has brought this process into sharp focus. Many of its observations have aligned beautifully with decades of astronomical predictions, confirming ideas about stellar evolution, planetary atmospheres, and the large-scale structure of the universe. Yet among these successes are discoveries that appear difficult to reconcile with current models, particularly regarding the earliest galaxies. These unexpected findings have sparked lively discussions throughout the scientific community, not because they invalidate modern cosmology, but because they expose areas where our understanding may still be incomplete. It is important to understand that science does not collapse when observations challenge theory. Instead, it becomes more active. Researchers begin by asking whether the measurements are accurate. They examine the instruments, repeat calculations, compare independent observations, and search for possible sources of error. In the case of Webb, scientists carefully analyze the light received from distant galaxies, measuring its spectrum to determine how far the light has traveled and how old the observed objects truly are. These methods help distinguish between genuinely surprising discoveries and interpretations that may change as more precise data become available. Even when observations are confirmed, the next step is not to discard decades of knowledge overnight. Scientists first explore whether existing theories can accommodate the new evidence through adjustments rather than complete replacement. Perhaps galaxies formed stars more rapidly than expected. Perhaps clouds of gas cooled more efficiently under early cosmic conditions. Perhaps interactions involving dark matter played a greater role than current simulations assume. Each possibility is examined through mathematical models, computer simulations, and further observations before broader conclusions are reached. This careful approach reflects one of the defining principles of science. Extraordinary claims require extraordinary evidence. A single surprising observation is rarely enough to overturn an established framework. Instead, scientists seek multiple independent lines of evidence pointing toward the same conclusion. If numerous observations continue to challenge existing theories despite repeated testing, confidence gradually shifts toward revised explanations. This process can take years or even decades, ensuring that changes to scientific understanding are supported by consistent and reproducible evidence rather than excitement or speculation. History offers many examples of this method at work. The unusual motion of Mercury eventually contributed to Einstein's theory of general relativity. The unexpected rotation speeds of galaxies led researchers to investigate the existence of dark matter. Tiny irregularities in the cosmic microwave background transformed ideas about the early universe and the formation of galaxies. Each discovery began as an observation that seemed inconsistent with accepted models before becoming part of a broader understanding supported by extensive evidence. The questions raised by the James Webb Space Telescope follow this same tradition. Rather than signaling a crisis, they demonstrate that scientific knowledge remains dynamic, constantly shaped by observation, experimentation, and critical analysis. Every unexpected result invites researchers to examine familiar ideas from new perspectives, improve theoretical models, design more sophisticated simulations, and search for additional evidence capable of revealing how the universe truly evolved across billions of years. Human knowledge is often imagined as a steadily rising tower, with each discovery adding another solid layer to an ever-growing structure of certainty. While this image is appealing, it fails to capture the true nature of scientific progress. A more accurate picture is that of an expanding frontier. Every answer pushes the boundary of understanding outward, but in doing so, it also reveals new territories of uncertainty. The greater our knowledge becomes, the more clearly we recognize how much remains unexplored. The James Webb Space Telescope has become one of the most powerful reminders of this principle, not because it solved every mystery it was built to investigate, but because it uncovered questions that few had anticipated. Before Webb began its mission, astronomers had developed detailed models describing the evolution of the universe from its earliest moments to the present day. These models were based on decades of observations, sophisticated mathematics, and powerful computer simulations. They successfully explained many features of the cosmos, including the expansion of space, the formation of galaxies, and the distribution of matter on enormous scales. Scientists expected Webb to refine these models by filling in missing details and providing higher resolution observations of the distant universe. Instead, the telescope revealed a landscape more complex than anticipated. Some of its earliest observations hinted that galaxies may have formed faster, grown larger, or organized themselves more efficiently than current theories predicted. Rather than closing the gaps in our understanding, these discoveries widened them. The questions shifted from simply asking when the first galaxies appeared to asking whether the physical processes driving their formation were more diverse and dynamic than previously believed. This pattern reflects a recurring theme throughout the history of science. Every technological breakthrough expands the range of observable phenomena, exposing details that earlier generations could never detect. The microscope revealed microorganisms invisible to the naked eye, opening entirely new fields of biology. Particle accelerators uncovered fundamental particles that reshaped modern physics. Space telescopes exposed galaxies billions of light years away, transforming cosmology into a science based on direct observation rather than philosophical speculation. Each new instrument expanded humanity's field of vision while simultaneously increasing the number of unanswered questions. The frontier of the unknown does not shrink as knowledge grows. In many ways, it expands alongside it. Every discovery creates fresh opportunities for investigation because each answer exists within a larger network of related questions. Learning how stars form naturally leads to questions about planetary systems. Understanding planetary systems raises questions about the emergence of life. Studying life encourages inquiries into consciousness, intelligence, and humanity's place in the universe. Knowledge unfolds like an interconnected web rather than a collection of isolated facts. The James Webb Space Telescope embodies this ongoing expansion of inquiry. Its infrared instruments allow scientists to observe ancient light with unprecedented sensitivity, revealing structures, chemical signatures, and distant galaxies that had remained hidden for billions of years. Each image contains enormous amounts of information, yet every measurement also introduces new puzzles requiring careful analysis. Astronomers compare observations with simulations, revise assumptions, and design future investigations aimed at explaining features that current theories struggle to reproduce. Perhaps the most profound consequence of Webb's discoveries is not the specific data it collects, but the reminder that scientific exploration is an open-ended journey. Every generation inherits unanswered questions from the one before it, while creating new mysteries for those who follow. The universe continues to reveal unexpected complexity whenever humanity develops better tools for observing it, ensuring that the horizon of discovery always stretches farther than our current understanding can reach. It is easy to think of mysteries as obstacles, as gaps in knowledge that exist only because humanity has not yet found the right answers. In everyday life, uncertainty often feels uncomfortable. We naturally seek explanations that bring order to confusing situations, and once a problem appears solved, we tend to move on. Science operates differently. Within scientific inquiry, a mystery is not viewed as a failure of understanding, but as a signpost pointing toward new opportunities for discovery. The questions that resist easy answers are often the ones that reshape entire fields of knowledge, leading researchers beyond familiar ideas and into unexplored territory. The James Webb Space Telescope has become a powerful example of this process. It was built to investigate some of the oldest questions in astronomy, including how the first stars formed, how galaxies evolved, and what the early universe looked like after the Big Bang. While Webb has already provided remarkable insights into these topics, some of its observations have also introduced puzzles that scientists did not anticipate. Rather than discouraging researchers, these unexpected findings have energized the astronomical community, inspiring new investigations, revised simulations, and fresh theoretical ideas aimed at explaining what the telescope has revealed. Scientific mysteries perform an important role because they expose the limits of existing knowledge. Every successful theory explains a wide range of observations, but no theory can answer every possible question forever. Nature is often more intricate than the models developed to describe it. When new evidence challenges those models, scientists gain valuable information about where their understanding may need improvement. Instead of treating these discrepancies as problems to ignore, researchers examine them closely, recognizing that the most significant advances frequently emerge from precisely these moments of uncertainty. History repeatedly demonstrates this pattern. The strange behavior of electricity and magnetism during the 19th century eventually led to a unified theory describing electromagnetic fields. Unexpected experimental results concerning the speed of light inspired the development of special relativity. Tiny inconsistencies in atomic behavior contributed to the birth of quantum mechanics, fundamentally changing humanity's understanding of matter and energy. None of these revolutions began with complete certainty. They began with observations that refused to fit established expectations, encouraging scientists to ask better questions rather than forcing reality into existing frameworks. The value of a mystery also lies in its ability to inspire collaboration across multiple disciplines. Modern astronomy depends not only on telescopes, but also on physics, chemistry, mathematics, computer science, and engineering. When Webb identifies an unexpected galaxy or detects unusual chemical signatures in distant worlds, experts from many fields work together to interpret the data. Computer models are refined, laboratory experiments are compared with astronomical observations, and independent research teams test competing explanations. Every unresolved question becomes a meeting point where diverse forms of expertise contribute to a deeper understanding of the universe. Scientific mysteries also encourage technological innovation. Throughout history, new questions have often required new instruments capable of making more precise measurements. Improved telescopes, advanced detectors, faster computers, and sophisticated spacecraft are frequently developed because existing tools cannot fully answer emerging questions. In this way, mysteries drive progress not only in scientific theory, but also in the technologies that expand humanity's ability to observe and explore the natural world. The discoveries made by the James Webb Space Telescope illustrate that every important answer eventually gives rise to new questions. As researchers investigate surprising observations, refine their models, and gather additional evidence, the process of discovery continues to expand, revealing an increasingly detailed yet ever more complex picture of a universe that consistently rewards curiosity with deeper layers of understanding. When we examine the breathtaking images captured by the James Webb Space Telescope, it is natural to focus on the galaxies, stars, and nebulae filling the frame. Yet these remarkable observations also tell another story, one that is less about distant objects and more about ourselves. Every image represents the outcome of countless generations of curiosity, persistence, and imagination. From the earliest people who wondered about the lights in the night sky to the engineers and scientists who designed one of the most sophisticated scientific instruments ever built, the telescope reflects humanity's enduring desire to understand its place within an unimaginably vast universe. The scale of that universe is almost impossible to comprehend. The observable cosmos stretches across roughly 93 billion light-years, containing hundreds of billions and possibly trillions of galaxies. Each galaxy holds immense numbers of stars, many surrounded by planets. Around those planets, physical laws shape environments ranging from frozen wastelands to scorching worlds dominated by volcanic activity. Somewhere among these countless systems, the conditions necessary for life may exist, while in many others, entirely different cosmic stories continue to unfold beyond the reach of present observation. Against this immense backdrop, Earth occupies an extraordinarily small position. Our planet circles an ordinary star located within one spiral arm of the Milky Way galaxy, itself only one galaxy among an almost unimaginable multitude. From a purely cosmic perspective, humanity appears insignificant in size, location, and duration. Our civilization has existed for only a tiny fraction of the universe's nearly 13.8 billion-year history. Entire galaxies completed major stages of their evolution long before Earth even formed, and the ancient light now reaching the James Webb Space Telescope began its journey billions of years before the first living organisms appeared on our planet. Yet this apparent insignificance gives rise to one of the most extraordinary realities in science. Despite occupying such a small corner of the cosmos, humanity has developed the ability to investigate events that occurred near the beginning of cosmic history. Through mathematics, engineering, physics, and international cooperation, people have built instruments capable of detecting faint infrared light emitted by galaxies whose existence was once beyond imagination. The atoms composing human brains originated inside ancient stars, and those same atoms have become capable of questioning the very universe that produced them. This perspective transforms our understanding of observation itself. Every photon collected by the James Webb Space Telescope has traveled across expanding space for billions of years before finally reaching its mirrors. During that immense journey, continents formed and vanished on Earth, countless species evolved and disappeared, civilizations rose and fell, and human knowledge expanded from simple observations of the night sky to sophisticated space-based observatories. The arrival of those ancient photons connects distant epochs of cosmic history with a single moment of scientific discovery. The telescope also reminds us that understanding our place in the universe involves more than measuring distances or cataloging galaxies. It requires recognizing the relationship between knowledge and perspective. Every discovery changes not only what we know about the cosmos, but also how we view ourselves. The realization that Earth is not the center of the universe transformed philosophy and science alike. Learning that the elements within our bodies were forged inside stars connected human existence to stellar evolution. Discovering planets around distant stars expanded the possibility that our world is one among countless others. As the James Webb Space Telescope continues exploring deeper regions of space and earlier periods of cosmic history, it reinforces a profound truth about humanity. Our greatest achievement may not simply be building machines that can see farther into the universe, but developing the curiosity to ask questions whose answers lie billions of years away, guided by the understanding that every new discovery reshapes the story of where we came from and how we fit into the vast unfolding history of the cosmos.